So this episode is focused on the dipole method. Last episode, I talked a little bit about all of the available electrical leak location methods, but this method really deserves its own chapter. In fact, there's going to be several chapters on this method because this is the real hard nut to crack. It's a very powerful method, but there's a lot of things that can go wrong. So for this episode, I'm going to focus on explaining how the method works physically, and then how ASTM D7007 details how to actually perform this method and how it establishes the success of this method. Included in that is different methods of data analysis that are all detailed in the ASTM. So I'm going to talk about each one so that we can kind of understand the advantages and limitations of each. So the last part is going to be focusing on how the sensitivity of the method is determined by site conditions, and also how to create better project specifications to support this ASTM so that we can maximize survey sensitivity. So this method is used for installed geomembranes that are covered with any semiconductive layer. So what do I mean by that? It doesn't have to be ultra conductive, like something like salt water. It can be anything like soil, sand, gravel, concrete, water itself. For the soil and the gravel and the sand, and concrete, you do need a certain moisture content to make those semiconductive. It looks like some folks are still having difficulty with viewing this through their browser. I would change your browser perhaps, and you can have better viewing of it. So ASTM D7007 is divided into two different sections. The soil covered method is on section 8. The water covered method is in section 7. It's the same principle. They're all the dipole method, but the procedures are just slightly different for water and soil covered. And part of it just has to do with the history of the technology and how it has evolved. It actually started with water covered methods and evolved to soil covered. So I'm also going to mention briefly, there is a new method that is currently a work item in the ASTM committee, and it will likely be published in early 2019. And it's also going to be method, it's basically dipole method for covered geomembranes, and it's an alternative to D7007. Today I'm going to talk about some of the issues that arise in D7007, and this new ASTM will address those issues. So let's talk about what a dipole is and how it got its name. So the dipole method is named after the measuring apparatus that is used during the dipole method. And what it is a structure with two measurement points. We often refer to them as feet just because it kind of looks like feet. So you have this measuring apparatus, you have a front foot, and you have a back foot. And then oftentimes you have string lines across the survey area to guide the placement of the feet as it travels throughout the survey area taking measurements. So in order to explain how this method works, I'm using a figure from my old friend Carl Charpentier, which many years ago, he was one of my first instructors. So basically, the easiest way to explain how current flows is to make the analogy to water. So if you kind of picture current as flowing like water, for example, current flowing through a conduit is like water flowing through a stream, down a stream. If you have a reservoir of water, this is like a dipole survey. So the water is sitting in the reservoir, and if you're pumping the water in on one end, you have a high point in the water elevations. So these equipotential lines are actually voltage lines. So this would be a given voltage. And it's a lot like if you were to make a topographical map of a water surface. So you'd have a high point where the water is coming in, i.e. the current's coming in. And if you have a leak in the survey area, you have a point where the water is exiting. It's a lot like taking the drain on a bathtub and taking the drain out, and then you get a funnel of water going into the hole. That's exactly what the voltage field does. And so the current is exiting the hole from all directions. And we walk around the survey area with this dipole. In the figure, you see a little guy with a double dipole. He's got a dipole on the left and the right, just to be more efficient. And he's measuring the voltage in the entire survey area. So let's talk about what he's actually measuring when he's walking throughout the survey area. So a dipole, going back to the analogy of the water surface, a dipole is measuring a gradient of the surface. And so if this bullseye pattern is the equipotential lines, it forms a bullseye around where a leak is, and the dipole measures the surface gradient leading up to that leak. So if we're measuring from the front foot to the back foot, you're going to get a negative value as you approach a leak, and you're going to get a positive value as you travel past the leak. And so this is what it actually looks like in the voltage values as you travel across this leak. Above, we have the dipole apparatus. It's going right past the leak, and we have the voltage plotted as it travels past that leak. Now, when the dipole has its front foot right exactly on the leak location, you get your highest magnitude of negative value. And then as it straddles the leak, it travels through 0. And then as the left or the back foot goes over the leak, you have your highest positive value there. And then as you continue on, the signal just kind of trails down to background values. So that leak signature, that sine wave pattern that we refer to, that's what we're looking for when we're walking out there and we're surveying the area. And these arrows just kind of show how you walk back and forth across the area in lines. And we're looking for that sine wave pattern in each one of those lines that would indicate there's a leak there. So the way ASTM D7007 works is that it establishes criteria for the distance between those lines of data, the distance between the survey transects. So it uses something called leak detection distance testing, and it has you walk a straight line past the leak at a certain offset, and you have to determine what offset will allow you to see where that leak is or deem it detectable. So as, for example, if you walk by the leak with a 20-foot offset, you may not see it. You walk past with a 10-foot offset, you'll see it a little bit better. If you walk with a 0 offset, you're walking right over the leak, and it's most detectable at that point. So in order to do this, we can either poke an actual hole in the geomembrane, or we can use what's called an artificial leak, which is a simulation of a leak. It's a round metallic conductive disc, but it's not an actual leak in the geomembrane. So this is what that looks like. You have a conductive metallic disc, and this one has a couple different sizes. So it's connected to an insulated wire, and this wire is connected to the subgrade somewhere outside of the survey area. It looks like we're having some issues with sound. I don't know if it's on my end or your end. So if you are not having issue with the sound, you could type in you're not having an issue, then we know that it's on the end of just a couple. Oh, sound is loud and clear. So it might be your internet connection if the sound is cutting out on you. So you place this artificial or actual leak in what we call the worst case scenario, which is right in between the measurement points. So we saw from that figure, when your foot travels directly on the leak, then it's the most sensitive, you get the largest signal. So when you're trying to determine how far away you can be and still see that leak, you want to create the worst case scenario so that when you actually do the survey, that you will find this target leak size. So what is detectable? What do we mean by that? Well, for soil-covered surveys, the ASTM came up with something called a signal plus noise to noise measurement. So this graph up here is if you don't have a leak in the area and you're just walking across in a straight line, you're going to have some variability in the voltage there. And then when you plug in the leak, you're going to see that sine wave pattern. So what they want you to do is measure the distance between the peaks, and they're going to call this magnitude from peak to peak the signal plus noise, and they're going to call the magnitude of the noise just plain noise. And for soil covered survey areas, you need for that R value, they call it the R value, which is, to say it in a quick manner, signal to noise ratio, but it's actually the signal plus noise to noise ratio. So that R value needs to be 3. So it needs to be significant, 3 times greater than the surrounding background noise. But for water covered, the ASTM simply requires that target leak size be detectable. What does that mean? It's usually just an increase in the audible signal as you walk past it. And as long as you would notice that increase in signal when you're doing the survey, then they consider that detectable. So the water cover method allows the grid spacing to be twice the leak detection distance, meaning that if we go back to that graph here, if this distance away that you detect the leak is, say, 5 feet, then you can do a grid spacing of 10 by 10 because you're never going to be greater than 5 feet away. But for the soil covered method, they have a safety factor in there, and they only allow you to be 1.5 times the leak detection distance. So what that means in practical terms is that if you want to do a measurement density of 10 feet by 10 feet, the offset when you're doing your leak detection distance test needs to be 6 feet 8 inches. In metric, if you're doing a 3 by 3 meter, the offset would need to be 2 meters. So now we'll talk about data analysis. So we've established the distance between our survey scans, but the ASTM doesn't require data recording for water covered surveys. It's just simply listening to the audible beeping. So you're just walking back and forth, you're listening for the increase in tone, and when you hear that, you stop, you locate the leak, and then you move on and continue the survey. It does require data recording for soil covered surveys, but they don't specify exactly what type of analysis you need to do for the data. It says at the very end of the ASTM in the report output that data should be provided in ASCII format if requested by the client, but ASCII format just simply means a list of voltage values as they were acquired during the survey. But now we know that any particular value is kind of meaningless. It really, it's the values in context. We're looking at shapes. We're looking for the sine wave pattern. It's not like any one value means something. So ASCII format is problematic because it's very difficult to review. Even me, if someone were to send me a list of voltages in a column, I still don't really know what I'm looking at because it's just values. You might be able to see some patterns in it, but I don't know if that's a leak or if that's the current injector or what. So there's 2 methods of data analysis that are presented in the ASTM that are meaningful ways to review the data. It refers to them as graphical and voltage contour mapping. So I am going to talk about all 3 of these types of data analysis. So we have the audible beeping, real time, and then we have the graphical and the voltage contour. So I have a video that I'd like to share because a video will speak 1,000 words as far as how the audio beeping works and how to notice when you get an increase in the tone and how that's actually done to go out and survey real time listening for the beeps. have maximum positive out there. So again, as we get away from the hole, that signal drops off. As we go toward the hole, this increase, directly on top of it. And if I travel across the hole, then it's going to give me the characteristic sine wave pattern. You now see in the graphic right there, the sine wave down and up. So hopefully you guys were able to hear that. I'm sure you were at least able to hear the beeping noise. So essentially, whenever that meter converts volts to voltage into when the voltage gets high, it increases the frequency of the tone. And so it will notice any kind of abrupt increase or decrease in the voltage. And by looking at the magnitude and the sign, you know that the largest negative is when your front foot's on the leak, and the largest positive is when your back foot's on it. So that's how you do the actual pinpointing. So this works fairly well if you're able to wade through the water, because you can move the dipole back and forth and get precisely where that leak is, and you can drop a weight right on that leak. But where this method gets problematic is when you have deeply filled ponds. So the way we survey deeply filled ponds is that we take a dipole and we attach it to a cable, we submerge it in the water, and we actually operate it from outside the pond. And we pass it back and forth across the pond, so it's traveling back and forth. And the operator on one side of the pond is listening for that beeping noise. So you can imagine how difficult it is when somebody's on the other end and you're pulling the cable, trying to go back and forth and left and right, trying to locate this leak exactly. So the biggest problem with this method for the deeply filled ponds is getting a really good accuracy in leak location. So for one thing, it's hard to tell exactly where your dipole is along that cable. And for the other thing, it's really hard to say where the peak is coming from when you're just passing the dipole back and forth, and it's really hard to maneuver left and right back and forth. So what you end up with, like for example, this survey where I got leak signals on 3 different lines, which could be attributed to 3 different leaks or one leak in the middle. And it's really hard to say where the strongest signal is unless you have some method of recording, and then you could perhaps label the flags of what voltage reading you got at each one so they can kind of guess where exactly the leak is. But it's very imprecise. And not only that, is I've never surveyed a filled pond that didn't have obstacles for the drag probe. So, you know, you're pulling the drag probe back and forth. There's bird wires, there's pipes, there's all kinds of structures in there in place, sometimes aerators. Sometimes you pull up bird carcasses and sticks and whatever's bottom of the pond. So it's just physically difficult to maneuver the dipole remotely like this. So going back to the evolution of this method, the water methods were actually developed first, and the audio beeping method was developed first. And then they said, hey, we can apply this to soil as well. But the problem is that you can't move continuously through the soil. Every time you take a measurement, you have to pick up the apparatus and move it and set it down again in order to see that sine wave pattern in the cover material. So they came up with the idea that they would require the data analysis so that they could convert this voltage into a visual cue that there's an anomaly there or potential leak present. So the 2 ways that you can take the recorded data and analyze it in a meaningful way are the graphical data analysis and the voltage contour map. So first I'll talk about the graphical data analysis. What's nice about this is that the way this is graphed is that it has each line right next to each other. And so you can actually see that leak anomaly. You can start to see it on this line over here, and it gets more and more enhanced. And then you can see that that leak is right closest to line 112.5. So it works to do this. There's no problem with plotting it this way. So it is one option. The other option is doing, this happens to be GPS based, but it doesn't have to be GPS based. You can also just create a local coordinate system with those same string lines. label the string lines, and then do data entry at the end of the project for the voltage and the XY coordinates. So this is what a map looks like. Let me explain how to read this map. So this big square represents the entire survey area. Your current electrode is coming in right here. And what the current electrode does is it polarizes the entire survey area because it's being measured by a dipole. So the entire top half will be negative in general, and the entire bottom half will be positive in general. And that's just simply because the dipole is walking this way, backwards and forwards, throughout the survey area, and it's always pointed toward the top of the map. So as it's walking this way, it's measuring positive voltages, and once past the current injector, it starts registering negative voltage values. So what we're looking for in a leak is the exact opposite pattern as the current electrode. See, current enters the pad via the current injector, and it exits the pad via the leaks. And so they end up looking like the opposite of the current electrode. So the current injector has positive on the bottom, negative on the top. The leaks have positive on the top, negative on the bottom. And they tend to look like butterflies because there's very closely shaped contours right where the leak is. And you can see bubbles where the peak of the positive and negative values are. So for this particular map, the dipole was walking this way. You can see one leak here and a smaller leak here. So that's how you read those maps. And the nice thing about it is you can see that the entire survey area was covered, and it's a really easy way you can have this map be reviewed by anybody involved in the project in like 5 minutes. Explain how to read the map, show them the data that was collected, and they immediately know if there was a leak or not in the survey area. So the ASTM allows for all of these different types of data analysis and whatever other kind of analysis you want to do. But the new GPS-based technologies really make the real-time data analysis less appealing, at least for me, and from the perspective of a design engineer or an owner who doesn't want to just watch somebody walking around in their pond or soil-covered area, just looking at voltage, and then you just trust that everything was done correctly. It's only reviewable by the person doing the survey. So even me as a manager of electrical leak location company, I'm uncomfortable, even with technicians that I know that know what they're doing. If they're out there just collecting data, I'm just trusting that everything went right. If I require them to record the data, produce a map, then I know exactly in one glance what went on in the field, whether they're out there, and whether it was done thoroughly and correctly or not. So you don't need the fancy GPS-based coordinate system. You can also create a local coordinate system, and really it's not that much different than the graphical survey analysis. It just adds a third dimension. It adds an X and Y, and then V would be the Z. So it's almost like a three-dimensional map. So this is a very simple way of adding the GPS component to water-covered surveys. I don't perform the beeping-based surveys anymore. I do sometimes the leak pinpoint, but for me, I really like to walk away from a project with a map of exactly what happened so that I can show and document exactly what happened during the survey. So you're still walking back and forth, you're still recording voltage, and it's just connected to GPS, so you can rapidly map it. As soon as you step out of the pond, you can take a look and analyze it for any anomalies that you might not have seen when you're actually walking through the pond. So it's a nice little addition. And then for these deeply filled ponds, all you have to do is establish a local coordinate system where you can either use survey lath or flags, some kind of marking, and then label it. And then also you have something attached to the dipole cable itself to tell you exactly where the dipole is at all times. So you start with the dipole at one end of the pond, and you call that your 0 in the Y direction. Let it out 10 feet, now Y equals 10. Let it out 20 feet, now Y equals 20. And it's fairly easy to keep track of these things and just make it part of your data recording. So this is it that came out of one of those deep pond-filled surveys. This is the current injector right here, and this is a leak right here. We can see it's the opposite pattern as the current injector. And it's kind of that butterfly shape. And the way you know that this is a local coordinate system and not based on GPS is that look at how perfectly all the little tick marks are spaced. This shows all of the measurement locations, and so it's way too perfect to be an actual GPS, which when you're walking with GPS, the locations will be off by a few inches, you know, pretty much every time. So transitioning from data analysis to what makes a survey sensitive. I'll tell you right now that sensitivity is 100% dependent on site conditions. The ASTM D7007 doesn't require proper site preparation. It details what should be done, and I'm quoting from the ASTM, if practical. So if practical, you isolate the cover materials from the subgrade. If practical, you need to, you know, add the adequate moisture. But in my experience, it's not an option. It's essential if you want actual leak detection. You have to prepare the site properly. So ASTM, it uses an increase in measurement density to make up for poor sensitivity due to poor site conditions, but it really doesn't work well. I know this from, gosh, 13 years of experience doing this. No, 15 years. So it just doesn't work. The R value that was written into the ASTM, even the original author of it said, well, we had to come up with something. We had to come up with something that shows that it's working. It's fairly arbitrary. It does not show the big picture results of the survey. I've been on sites where a 3-to-1 signal-to-noise ratio, you know, worked. You could see it very well, and other sites where you couldn't see it very well. So it's really not a good measure of how detectable a leak is. So, so these are the 4 criteria that are just required for leak detection. The cover material inside of the survey area must be electrically isolated from the underlying semiconductive layer. Usually it's the subgrade, and so it's the surrounding rock. For a single line geomembrane, it would just be the ground outside the survey area. The cover material has to be adequately electrically conductive, and the material below the geomembrane must be electrically conductive. Any leaks in the geomembrane have to have good contact. So what that means that, you know, a hole has to be large enough for the soil to get through the hole, for the cover material to actually be touching the subgrade, or you need to have a lot of water, and so there's moisture going through that preparation. So in summary, you have to make sure that the current is able to travel through all of the materials and through the leak and only the leak. You want to force the current to go through the leak and no other place, and that's the only way to be sure that you're going to pick that leak up. So what are we talking about isolation? So in this photo here, we have the survey area on the left. We have this gravel here is connected to the surrounding ground, and so we have to create isolation between the area where we're working and where we're charging up with the current. We're grounded to this soil out here, so we want to leave this isolation trench to force the current to go through the leaks and not just through the cover material to return to the ground. So very often we have to water the cover material during the survey, and we want to drive a water truck on there, but we can't just put an access road in place because all the current is going to travel from inside to the outside via this access road. So one nice thing we could do is actually add an isolation flap that bisects the road completely. So that allows trucks to go in and out, but it's also providing electrical isolation. Watering the cover materials is a very common thing we need to do, especially in arid climates. The subgrade is hardly ever a problem. It's never been a problem for me. Usually there's enough moisture just in the natural soils to be conductive. Unless it's a double line facility, and that's a GCL between those 2 geomembranes, then you might have to moisture condition the GCL. So the way to understand how this works is that electricity follows the path of least resistance. There's no way around this. This is physics. So if your cover material is not isolated from the surrounding ground, you're going to have a really hard time forcing the current to go through a leak. the more electrical pathways there are for the current to travel, the less is going to go into any one pathway. Dipole testing is going to find the most significant current leaks and may or may not find the areas of lesser current leakage. So at sites with excessive current leakage, this could be excessive holes, or this could be water ponding around the dirt and compromising the isolation. It could be access roads in place. You'll see all of those biggest current leaks, but you may not see all the holes in the lining system. So if you do a survey that's perfectly isolated around the perimeter and you don't have good sensitivity, you definitely have a leak in that lining system. So you may, if you have large leaks, you may need to actually find those, uncover them, dry them out, and then resurvey in order to find the smaller leaks. So in summary, the more isolated the site around the boundary, the fewer the leaks, and the wetter the survey area, the more sensitive the survey is going to be. So this is an electrical diagram of what's going on. We have our DC voltage source. We have a positive terminal and a negative terminal. We're forcing that current through the cover soil, so this must be adequately moist. And then that current can travel through any one of these legs. We might have 3 different holes. We might have some perimeter soil where the soil is bridging to the outside. And the electricity can travel any and all of these paths. But then it must go through subgrade. So we do need adequate connectivity in our subgrade, and it will do anything it can to get back to that ground. So I'm going to go through some case studies that illustrate all the points that I just talked about. And I'm going to start with a couple of sites that had very good sensitivity and explain why they had good sensitivity. So at this particular site, you can see the tick marks where we have measurement locations. These tick marks are spaced 10 feet apart. And so at this particular site, we found 2 pinholes from GCL needles. This first location, the needle was sticking through the geomembrane. We couldn't see anything at first, but you put your finger on the geomembrane, you got a little bit of a prick on your finger. The second location, it was just a pinhole, but there was no pin anymore in it. So it was like a needle had gone through and then gotten lost. So it was an actual just pinhole. But you can see how sensitive this is because 10, 20, 30, 40, 50, you can easily see a pinhole from 50 to 60 feet away. So that's really great sensitivity. At this particular site, it was the rainy season in China, and we also watered heavily during the survey. The cover material was gravel, and so it readily allowed the water to go right down to the top of the geomembrane. Therefore, those pinholes were actively leaking as we were doing our leak location. So that's one way to get it very sensitive, is to cause the holes to actually leak. At this particular site, we used the double dipole technology where we can measure not only in the direction that we're surveying, but also the perpendicular direction. Let me go back to this slide here. When we're surveying, we're walking backwards. We're walking forwards with the dipole, but we're going backwards and forwards across the survey area, looking at the voltage across the left side and the right side. But in the background, every time we hit the record button, we're also measuring the voltage across the front feet and the back feet. And so we actually produced 2 maps for the price of 1, essentially. And the thing about leaks is that you have to travel across a leak in order to see it, in order to see that sine wave pattern. Otherwise, if you only just walk up to it, you only see half of the sine wave pattern, and it's much harder to see. So at this particular site, let's call it the survey direction map, is shown in the background, which you've already seen. And then the perpendicular map, this is across the front legs and the back legs, dipole is shown here. And so this is our current injector. We got positive on the left, negative on the right. So what we're looking for is negative on the left, positive on the right. And then we see it again here. But then we see this hole right here that doesn't barely show up on this map. You can actually see it. There's a little negative peak right here, which is easy to miss because it's a negative peak in a negative area. But once we plot the perpendicular file, we can easily see that leak pop up because it's essentially like taking a dipole and walking along the edge here. So the important thing to realize is that the ASTM doesn't address this, but you have to walk across the leak in order to see it. So you can miss leaks if you're always approaching an edge and you're never walking parallel to the edge. This is another site that had fantastic sensitivity. This map is about 22 acres, and all of these little dots are spaced 10 feet apart. And so this leak right here, you can see 10, 20, 30 to 40 feet away. This particular leak, I put a flag in the ground and came back about half an hour later. They had excavated a big area liner, and they said, okay, where's your leak? You said it was here. And I said, well, where was my flag? And he said, right here. And he showed me with his foot. And I got down on my hands and knees, and I took my rag out of my bucket, and I cleaned it off and poked around with my fingers and found a knife slice that was about the size of my pinky, that you couldn't even see when you were standing right on top of it. So the key to this site's sensitivity was that it was really wet. So both of these sites that I'm talking about had perfect isolation. So the contractor did a really excellent job of making sure there's no soil bridging from the inside to the outside. And then also we were just lucky with the rain. So this particular site, it rained a day or two before I surveyed. And you can tell because these anomalies from pipe networks, this was standing water in the leachate trenches. You can see there's a trench there, there, there. It's almost like stripes of anomalies, and that's water standing in the trenches. So standing water head over the geomembrane will give you fantastic sensitivity. This is a case study of a site that had really bad sensitivity. This is about as bad as it gets. We see the map parallel to the survey direction here, and we kind of see this butterfly shape here. We see a bubble here separated by contours, so that kind of sticks out to us, but we never actually see the positive negative shift. But then when we look at the perpendicular map, we can see that positive negative shift. So we're looking for a negative on the left, positive on the right, and we can just barely see that. This particular hole is a 24-inch rip, and you could barely see it in the data. Another note about this mapping is that some leaks are easier to see in one direction versus the other. And sometimes when you're too close to the current injector, it's actually harder to see a leak. This map on the left, the reason why it's so hard to see this leak is that this area here is so negative because all the current is flowing. This site had poor isolation, so all the current is flowing right past that leak, and it's creating a large negative area. So even though that sine wave pattern is there, we don't see it because it's all shifted negative. So the sine wave pattern's there, but all the values are negative, so it's just really hard to see. So the problem with this site is that we had this wet sand material and we had concrete, and the geomembrane is fastened to the wooden board here with a batten strip and bolts. And this wood got completely waterlogged, so it became completely conductive. So we have really wet sand sitting up against waterlogged wood, bolted to concrete, which is grounded. So it had zero site isolation. So it's a miracle sometimes when these methods work when we don't have site isolation. Sometimes it happens, but they never work as well as they could. This is a case study from a blind leak test pad where the owner wanted to make sure that this method was going to work for large-scale facilities, so they built this test pad. So I came out with my mini dipole there, and the engineers poked some holes in the test pad area, and they wanted to see what I could find out there. So I mapped the site with my GPS, my double dipole. This was half of the site. This was, let's call it the north side of the pad. So we found this damage right here, this damage right here, and this damage right here. And the south side of the pad, we found this damage here and this damage here. Now we dug down to all the damage, we cleaned it off, isolated it, and then I resurveyed the entire pad. We do this per ASTM. When we find a leak, we survey just around the leak, like 15 feet or so around it, to make sure that leak didn't mask any other leaks nearby. But I know from experience, especially with a small area, that one leak in the survey area will mask any leaks in the area, or it can mask any leaks in the area if it's large enough. So I remapped the pad, and I found a huge anomaly right here. And let me go back to this first map here. This anomaly is right at 3545. This anomaly was sitting right here, and it was completely undetected in the first survey because those 1, 2, 3, 4, 5 points of damage that we excavated were drawing all the current in the area. So let me go back to the photo of the site. This leak was located here, so it's the smallest leak located in the thickest area of the pad. So it wasn't until after we excavated all this other damage that that little tiny half-inch diameter leak actually shows up in the data. And when we force the current to go through that leak, it shows up even just as well as a dozer tear, because we're forcing all the current to go through that particular hole. So going back to the R value, this is just, I have hundreds of sites of data that show the same thing, where we make a map that includes our artificial leak. We know what the R value is because we calculated it per the ASTM. We just don't see things lining up. It's not linear. So this particular site, I had really nice sensitivity. Each one of these little tick marks is like 10 feet, so 10, 20, 30. You can see that leak artificial leak from about 30 feet away. This is the exact same artificial leak at a different site, and you can only see it about, 8 to 10 feet away. But the R value that was calculated for the site on the left was 7.2, while the R value on the right was 17.6. And you think, how can that be? Well, think about it. Part of the equation is the noise in the area. So if you have a site that's really noisy, for example, the site on the left, I found a fairly large actual leak in the area. If you have a lot of noise, that is going to be part of your noise measurement. And so your signal is going to seem that much smaller. So the R value is a really simple, it's a gross simplification of what it requires to actually detect a leak. So, so going back to this concept of detectability, we're moving towards the looser concept of however you're doing your data analysis. If you can detect that target size leak in your mode of data analysis, that is considered detectable, much like the water-based methods detailed in the ASTM. So this is a map. You can see the tick marks in the survey area of a site where we left the artificial leak plugged in, so you can see it there. You can see it there from 10, 20, 30 feet away or so, and then some actual leaks that were detected. But this is also a way of showing detectability. We can still report the R value, but to me, this is a much better way to show that it's actually working. So going back to measurement density and what that means from a practical standpoint when we're doing this test, from experience, I just know that a 10 by 10 grid can practically always be used for properly prepared sites as long as they don't have excessive holes. Both the sites I have in mind where they were prepared perfectly and this measurement density did not work, both of them were riddled with holes. So the ASTM says if you aren't able to calculate a signal-to-noise ratio of 3 or an R value of 3 at all, no matter what the offset, then you should just perform the survey at a 1 meter by 1 meter grid, regardless of whether or not you can actually detect a hole in the lining system. So, and from a practical standpoint, if you go from a 10 by 10 grid to a 5 by 5 grid, that actually quadruples the time it takes to perform a survey. Going from a 10 by 10 grid to a 1 by 1 meter grid takes 9 times as long. So that means if the leak location survey is not working well due to poor site conditions, the survey will cost many times more, take a whole lot longer, and your results at the end may not be valid. So there's probably a reason why the ASTM is organized this way, but I don't think that it's a good one. First of all, a lot of these projects are lump sum bids, so somebody bidding on this project has to assume the measurement density because you can take a site that might take 1 day at a 10 by 10. It takes 4 days at a 5 by 5, and it's going to take 9 days if you have to go to 1 meter by 1 meter. And you really don't know until you're on site if that measurement density is going to work at that site or not. So, let's take a case scenario of you have a perfectly isolated site, but your sensitivity is still poor. So, is it better to do one 10 by 10 survey and locate the damage and then repeat a 10 by 10 survey, or do one 5 by 5 survey that's going to take 4 times as long and do the whole thing with less sensitivity? So we had a case like this very recently, actually. The site was perfectly isolated, and well, it had a couple issues because it was a really wet site. But we had poor sensitivity, but we just passed the leak detection distance test for a 5 by 5 grid. It's a fairly large site, 18 acres, and so we did the entire first half of the survey at a 5 by 5 grid. So that should have taken 1 day, and it took 3 or 4 days. By the time we got to the middle, we found 2 really significant locations of damage. This is one of them in the photo. And so what we did is we uncovered those sources of damage, and then all of a sudden a 10 by 10 grid worked just fine. And we're able to survey the remaining half of the site at a 10 by 10. The reality is that if we had just performed the first half at a 10 by 10, uncovered the damage, we could completely repeat the testing at a 10 by 10 with a better sensitivity for less than the cost of doing the 5 by 5, even though it was just on that first half. So we're talking about changing from quantity to quality, fixing the problem with the site rather than just increasing the measurement density. To me, it's like putting a Band-Aid on a broken leg. It's like you're trying to do something to make up for a bad situation rather than fixing what's actually wrong. So the biggest lacking of the ASTM D7007 are these 3 things in my mind. Proper site preparation. It should be absolutely required. When the site conditions are poor, the ASTM asks you to increase the measurement density. This gets really expensive for everybody, and it could be an issue with the schedule, and it doesn't make a big difference in sensitivity. It also does not talk about serving parallel to each edge of the survey area. You could miss holes if you don't survey along the edges. Those of us that have been doing this for a long time, we know this and we do this, but something that should be covered in the standard. The last one is presentation of the data in a meaningful, and by that I mean reviewable by you format. There's no point in recording data and presenting it at all if it's not meaningful and reviewable. So it should be presented in a way so that it can be easily reviewed by a third party. And just a note for you guys, the new standard that's on the ballot for the ASTM that hopefully will be published by the beginning of next year covers all of these things and makes it absolutely necessary as part of the method. So because we have these issues with the ASTM D7007, it becomes really, really important to write good specifications. You don't have good specifications and you just say ASTM D7007, almost anything can happen out there, and your survey can go from 0% to 100% effective, just depending on the contractors involved, really. So let's talk about what good survey specifications need to cover. First of all, site and design specific isolation. That's a #1, because everything else can kind of be done afterwards. If you don't address how you're going to isolate the cover material from the underlying layer as part of the construction design and schedule, you might be in a really bad situation when you don't have isolation and you have to do something like dig an isolation trench or perform the survey anyway at an increased measurement density, which is going to cost 9 times as much and also not be effective. Address moisture content of the cover material and, where necessary, the underlying layer. So usually subgrade is fine. If you have GCL encapsulated between 2 geomembranes, then you absolutely need to be aware of the moisture content requirements. Consider requiring either GPS-based data recording or just local coordinate system data recording and a voltage map as part of the report output. requires surveys parallel to every edge of the survey area, because that's where leaks can be missed. And I'll tell you, it's uncanny how often we find leaks on the edges of the survey area. I think maybe just increased traffic there. I don't know, but we find them all the time. So the other thing that's really important as a design engineer is that you do need electrodes in your underlying conductive layer for double line facilities. It's very easy to lay it out during construction, not so easy sometimes after everything is built. But the most important thing is just get the ELO contractor involved with the project from the beginning and get their advice on what needs to happen with the project from that point. So the thing you should not do with survey specifications, and this is just something that I've seen over the years, don't specify the hole size. The ASTM covered that, and it's also dictated by site sensitivity, site conditions. If you want to find leaks smaller than 6.4 millimeters, aka 1/4 inch, then you should specify a bare geomembrane survey right after geomembrane installation, and then you just follow it up with the dipole method survey to find any leaks that were caused during cover material placement. Don't specify a measurement density. I've seen this before. It's very strange, but you know, if you can detect a leak from 50 feet away, why would you do anything less than a 10-foot grid spacing? So don't reiterate things that are already spelled out in the ASTM. I've seen people try to do this and they don't cut and paste very well, and it just gets kind of butchered. It makes no sense. And then this thing is going back to the original design, is in general, you don't want design features that, if you want to do ELL, you have to think about that in the design. You don't want like a ductile iron pipe sitting on your cover material, bridging from the inside and outside. You have to think about these things and how your design is going to allow the ELL to be effectively carried out. And don't cut and paste the specification from the internet. I can't believe I have to say that. I've seen it so many times, I have to say that. So there's really no reason. If you feel like you don't know enough about this stuff and you need to cut and paste from the internet, just refer to the ASTM, and that's better than a cut and paste specification. So in conclusion, we talked about how this method works. We talked about how D7007 goes through the leak detection distance to determine your grid spacing, but there's so many crucial details that it allows to be optional. So it really doesn't provide enough rigor in itself for 100% testing success. So that's where we really need specifications and guidance. So it's really required for as long as ASTM D7007 is used. The success of a survey is not just dependent on the ELL contractor. It's a joint effort between the design engineer at the beginning, CQA firm, general contractor, and ELL contractor. If not everybody is on board, something bad is going to happen. So again, the effectiveness of this method can be 0 or 100%. I know it sounds crazy, but it's true, and it really depends mostly on site conditions. You can do the exact same survey in the exact same manner at 2 different sites. The one that's prepared properly, you will be able to find all the leaks. The one that's not, you may not find anything, whether they're there or not. So proper site preparation is really key, especially to dipole survey sensitivity. And cooperation planning is really the way that you're going to get to the proper site preparation. So I'm going to open it up for questions now, but also remind all you guys that we do have a full 2-day class on electrical leak location that happens usually twice a year. This year it's coming up in Austin, Texas, May 7th and 8th. That's coming up very soon. I think it's 2 weeks from now. So anyway, if you want to learn more about these methods, then it's something you should look into. And I encourage you all to ask questions at this point. If you have questions in the future, you're too shy to ask now, then you can always email me, aback@trienv.com. I'm not always available by phone, but I can practically always return emails within 24 hours. So we got a question: does the Dipole method work for compacted clay liner that constructs without geomembrane? So all of the electrical leak location methods that we have standards for are for installed membranes. So the way it works is that the geomembrane is electrically isolative, and so the current won't flow through the geomembrane, it will only flow through the leaks, and so we're tracing those leak paths. So it doesn't work, it's not going to find like short circuiting and compacted clay layers. That would be a different geophysical method. You have to have an installed geomembrane, and we're specifically looking for holes through the installed geomembrane. So another question: does the method work for conductive geomembranes? It depends on what you mean by that. If the geomembrane itself is overly conductive, then it may not work. We have developed methods that work on EPDM. If you mean conductive backed geomembrane, absolutely it works for conductive backed geomembranes, and we ground to the conductive backing on the HDP geomembrane. However, when you install that conductive backed geomembrane material, if you don't isolate the overlap flaps in a proper way, those overlaps can conduct, they can be a short circuit and a ground that carries the current from inside the survey area to outside the survey area. That's a whole different topic. In fact, at the upcoming ASTM meeting, a guide is going to be drafted on how to install conductive backed geomembrane that electrically isolates it in order to enable all of these methods. So can you comment on typical costs? Yeah, so the typical costs really depend on the method. I can tell you specifically the dipole testing, especially if you can count on a 10 by 10 grid. As you can imagine, if it takes 1 day on a 10 by 10, it takes 9 days. If I have to go to 1 meter by 1 meter, it's a very different cost difference. But typical cost for the dipole method, as long as the site is prepared properly, you don't have issues on that front, it's very approximately $1,000 an acre for a medium-sized site. So like about a 10-acre site will probably be somewhere around $1,000 an acre. But once the site gets smaller and smaller, it costs more per acre. So, you have a mob cost and you have a daily testing cost. So a 1 acre facility might cost the same as a 4 acre facility because it's mostly mobilization and setup. So, but to give you an idea, yeah, $1,000 an acre, and if you have something greater than 10 acres, it should go down from there. And for very large sites, I imagine it could go down to $500 an acre for very large sites, like 100 acres or more. And give it a couple more minutes to see if any other questions come through, and then I'm going to hand it back to John for the closing. And
all right.
Just go.
Thank you, Abigail. What we saw there was Abigail's going to be teaching a hands-on class in Austin, Texas in a few weeks. I've done the class before. For those of you who have never been out to do it, it is worthwhile, and it really helps to bring everything together when you can lay hands on this and pull it all together. Our next webinar is going to be at the end of May, and it's going to be given by Marcus Wilkie of Husker, Germany. He is an erosion control expert, and he is going to start a series on talking about erosion control products, design, implementing, and getting them out there. When we were talking about courses to offer to people, we felt that this one was strongly needed, and to help everybody get a handle on erosion control products that they're using at their sites. With that, we will conclude the webinar, and we look forward to seeing you all at the next one in May. Once again, thank you, Abigail, for doing this, and we are looking forward to your third webinar in the series.
Thank you, guys, and especially thank you all for attending. You guys are what we're here for, so thank you all.